Alright, so now we're going to focus in on these side chain properties. And the first breakdown is you can have kind of hydrophobic and hydrophilic side chains. So we still have the same backbone of amino acid, and no matter what the side chain properties are, that amino acid individually is going to float around freely in the cell. But this idea of side chain properties will become important as they become chain. Those side chains start to interact with each other, they start to interact with the environment, and the chain just is kind of it's just the linkage. So those, as you polymerize, the amino groups and the carboxyl groups become less important because they just start becoming connected train cars. So we'll talk about that more in the next video, but I just want to give you kind of an idea of why we're talking about this, and this idea of side chain properties will actually be really, really important when we talk about proteins in the next section, because these side chain properties drive the formation of protein and a protein holding its shape, as well as potentially the protein actually performing its function. So form and function are intrinsically related with proteins. If they're not the right shape, they tend not to do the right job. So they have to hold their shape. Side chain properties help them hold their shape, so they actually help them perform their task, as well as being just directly involved in what we call the active site. But we'll talk about that later. So just be aware that these ideas, this is not a one-off. This is something we're going to be circling back to a lot in the next section. And a really big one is you can have hydrophobic side chains. And what that means is that R is nonpolar. So for example, we could have something like amino acid called alanine, and I'm going to draw these in their Zwitter ion form, because why not? And so first off, this doesn't change. We've got the backbone. What does change? Well, now I'm going to start actually writing what R is. So this is called alanine. This is a specific amino acid. And if we look at just the R group here, it's all nonpolar. Water is polar, this is nonpolar. It's not going to really want to interact with water. It's not going to be water soluble, just the side chain. Now the whole thing, to be clear, the whole thing still floats around. But once we start linking them up, this side chain is going to want to interact with other nonpolar stuff. And that's a really important detail for later. We can have another example here. Another nonpolar side chain. And so, by the way, nonpolar, hydrophobic, they basically mean the same thing in this context. This is the simplest amino acid. The R group, the side chain, is just one hydrogen. It doesn't get any easier than that. And this is called glycine. Now, you don't have to memorize any of these structures. The key thing is, could you identify that this is a nonpolar side chain? And so you just ignore everything else. You ignore the whole backbone and you just go, oh, I've got a hydrogen bonded to a carb. That's a nonpolar bond. That's a nonpolar side chain. That is hydrophobic. That's what we're looking at there. Now, if we can have hydrophobic, well, then you can have hydrophilic. So this is like water-fearing, like you have like arachnophobia. Then you are afraid of spiders. This is like it's afraid of water. It doesn't want to interact with water. Hydrophobic. Hydrophilic, what's a good term for this? Like audiophile is like someone that's super into music, like they have, I don't know, $1,000 speakers, or the $100 ones that are basically just as good if you talk to those people. And that means that they like music. So phile means like, phobic means doesn't like. So we can have hydrophilic. Let's see, I gotta check my notes, make sure I spelled it right. 1L, okay. I can never remember. So we can have hydrophobic side chains. Now we're going to talk about hydrophilic side chains. Now, let's take a second, let's pause. Now, if a hydrophobic side chain has a nonpolar side chain, if R is nonpolar, what do you think that means for hydrophilic side chains? What's going to be the opposite of nonpolar? Yeah, so we're going to have a polar side chain. Okay. And So an example of this might be serine, which is another amino acid. So as we change that R group, we get a different name. Every amino acid should have a different name than the other amino acids. That'd be really confusing. We got two alanines, right? So we got alanine, we got glycine. Now we're going to draw serine. Guess what I'm going to start out drawing? Right there. That's not changing. All it's going to change is what I put above it. So I'm still going to have H3 N plus CH COO minus. Okay, right there, that's enough to tell you this is an amino acid. And then I'm going to have a CH3OH. So what I have is an alcohol group. I have a carbon with an alcohol group. That's going to make this polar. And you don't have to memorize the name, but I like to write the names. This is serine. Serine, introduce yourself to everyone. Okay. So we've got a side chain with some alcohol here. This is going to create a polar side chain, which means it's going to be hydrophilic. And not only is it polar, but look at that. You get hydrogen bonds. So you're going to get some even more favorable interactions with water, because water is a polar molecule, but it is also a hydrogen bonding monster. Okay, it is like 100% hydrogen bonds 100% of the time. Like it can hydrogen bond, it can send to, it can receive to. It is incredibly effective at hydrogen bonding, and so that's going to be an even stronger, more favorable interaction as well as the polarity. So you get a really nice matchup of attractive forces. They didn't go away, just like atoms definitely didn't go away. You know, these condensed structures clearly didn't go away. So we're just building on these ideas, and so these ideas of attractive forces are going to come into play big time with these side chains. And another example here, since I seem to be doing two at a time, why not draw another? I bet you can draw the backbone right now. Pause it, take a shot. Don't worry about what the side chain is yet, I'll tell you. Alright, so we've got our backbone here. So it's like, oh, boom, that's an amino acid. So instead of an oxygen, we have a sulfur. And so this is called cysteine. So every now and again, sulfur will mix in with organic compounds. It's not as common of a functional group, so we didn't worry about naming it, but it's a thiol group. Like this is an alcohol when it's an OH, when it's an SH, it's a thiol group. And there's another key detail with this that we will talk about in the next video as well. So it's good I'm showing you cysteine now. But this is polar. It's not necessarily a hydrogen bonder, but it's polar, so it's going to interact favorably with water. It's hydrophilic. So we have two polar side chains here. There are more. I'm not showing you all the amino acids. I'm just showing a couple examples. And so if you were asked, shown an image, first, is it an amino acid? Look at the backbone. Second, would this be a hydrophilic or a hydrophobic side chain? Well, then you got to look at the side chain. Because if you look at the whole thing, you go, oh, well, they're all hydrophilic. Yeah, overall, when you have this guy. But when it comes time to put these together, these side chains start to interact with each other indirectly through attractive forces. So we covalently bond the chain together, but attractive forces drive how that chain behaves and becomes a 3D structure and stays that way. Now there's a couple more properties to talk about, so don't worry, we're not done yet. We've also got acidic side chains. As you can clearly see. And there's a couple things here. So one, it means that there's a carboxyl group on the side chain, right? Carboxylic acid. So every amino acid has a carboxyl group. Not all of them have them on the side chain though, but some do. The other detail is that this is at physiological pH. So these are going to be anions at physiological pH. Just like the main backbone is for an amino acid. So they're going to have negative charge. Kind of dressing up a lot of language here. But remember, anions are negative charge. So, let's give an example here. We need a little bit more room. These side chains start getting a little longer. Just a heads up on that. So, backbone. Doesn't change. That's an amino acid. If I draw something else, it's not. It's not an amino acid. There's always the one exception. There's one that has like a weird ring because it interacts with side chain. So if you look up pictures of all the amino acids, you'll see that one. I'm not gonna hold you to that. Don't worry. There is an unreacted form where it would have this with a side chain. Anyway, this is all I expect you to know. But if you do look up the table of all the amino acids, I am aware that there's one that breaks this trend. Because there always is, right? But hey, we're an introductory class. Don't worry about it. So, we're going to have a CH2 group to start out. And then we'll have our COO minus. Okay? So there's 2 carbons in this chain. We just have a regular carbon with hydrogens. And then, boom, there's our carboxyl group. And at physiological pH, it's missing the hydrogen. So it's not COOH, it's COO minus, because that H pops off as an H plus, and it leaves behind the electrons that were used in the bond, and so it leaves a negative charge behind. And so what we're looking at, to be clear, is you've got your carbon, it's making a bond, it's got an O group, and so now that O group has 3 lone pairs. That's what we're looking at there. I probably should have showed that earlier, whatever. That's what this is. If we look at it in a little more detail. I am a lazy chemist. That's what I'm going to draw. But be aware that that's what's happening. So there should be a bond to an H here, but that has been taken away by the environment, having a lack of H's, H pluses. So it starts taking them from other locations, like carboxylic acids. And you don't need to know too much about that right now. All you got to remember right now is 4 amino acids. Carboxyl groups become negative. Amino groups become positive. And so this is what we call an acid. This is what we call a base. Acids are the opposite of base. So if I'm talking about acidic side chains, guess what I'm going to talk about next? Right? I had hydrophilic, hydrophobic were opposites. Now I've got acidic, and I'm going to talk about basic next. And so all you're looking for, if there's a carboxyl group, it's going to have an anion for a side chain. It's going to have an anionic, negatively charged side chain with a carboxyl group that got, what we say, deprotonated, but just became a negative charge. That's going to be really important because remember, ion-ion attractions are really strong, stronger than hydrogen bonding. So we can get that in these covalent molecules. We can have parts that are attracted or repulsed from each other because of full ionic charges, which is amazing. So, let's see. I said I would do 2 for each. This one's going to be a bit of a doozy. I think I give myself enough room. I gotta leave room for the other ones here. Okay, let's see if I can pull this off. Challenge accepted. Alright. So again, nothing changes on the backbone, but now I've got to squeeze in 2 CH2 groups here. Oh yeah, I can pull this off. Alright, and so this is glutamic acid right here. I forgot to name the other one, so give me a second. Okay, and so then we have aspartic acid, was the first one, since I said I would write the names. And so again, we see a carboxyl group on the side chain. That's a carboxylic acid, and it's going to become an anion at physiological pH. So let's talk about the opposites. Let's talk about basic side chains. So you have acids and bases. They're opposite friendships. It's not like these are simpler. It just means that they have a base in them. And so what this means is there's an amino group, or an amine, on the side chain. Okay? And so these are going to be cations at physiological pH, because that's what we've seen here. So we've already seen it a bunch. So all we're doing is taking this trend and we're moving them up here. That's all we're doing. We're moving them to the side chain. So before we got negatively charged stuff, now we're going to get positively charged side chains. So we're going to get the opposite anion, or sorry, the opposite ion, opposite of the anion. Yeah, two negatives makes a positive, right? Anyway, these side chains are, I don't know if I give myself anywhere near enough room to draw these. Okay, so, this is going to be close. Alright, I'm going to have to start way down at the bottom of my paper here. Last one I was worried over nothing. This time you'll see I'm legitimately concerned about my ability to fit this on the paper. Alright, I'm going to have 1, 2, 3, 4 CH2 groups. Starting to see why I'm worried now. 1, 2, 3, 4, and then attached, I'm just going to have to go sideways here. Attached to that CH2 group is an NH3 with a plus charge. So there's our amine. I apologize. I just ran out of vertical space. I should have drawn these all the way up. But anyway, this is called lysine. It's a different amino acid. It gets a different name, right? And one more example is... Ooh, man, I don't know if I can fit that one at all. Alright, well, you know what? I'm going to see this through to the end. I got a little more room here, so if I sneak down, I go CH. Okay. I've got 1, 2, 3 CH2s. And you're thinking, well, you just fit 4. What's the big deal? Well, there's more on top of these. Then I've got an NH, and then that goes to a carbon, which is double bonded to an NH2 that's positively charged, and then it has an H2N as well. Okay, and this is known as arginine. Arginine. Alright. We're going to say that that was a achievement unlocked right there. I managed to fit that on the screen. Anyway, all you're looking for, just to be clear, acidic is going to be negatively charged. You know that because you've seen it in the backbone before. It doesn't change just because there's a carboxyl group up here. So you just look for carboxyl groups. Basic side chains are going to be positively charged, and you're just looking for nitrogens. That's all it boils down to. Look for nitrogens in the side chain. Whether it's acidic or basic, it is hydrophilic. It's going to interact very favorably with water. But they're also, if you have pairs, they're going to interact extremely favorably with each other. So if I have an anion and a cation, they can be attracted to each other. And this can be a very key idea because maybe they're very far apart on the chain, but the chain can fold around, and then these groups help hold it together with a very strong interaction. More than hydrogen bonding, which is also very important in the process of what we're going to talk about. But yeah, so these are the key details. Is it acidic? Is it basic? Is it hydrophilic? Is it hydrophobic? That's all you got to know. So those 4, and it's just basically 2 pairs of opposites. Is it hydrophilic or hydrophobic? Is it acidic or basic? That's all it boils down to. And these fall under the hydrophilic category as well. So these are like subcategories of hydrophilic. Now, not everything that's hydrophilic is acidic or basic, right? I showed a couple examples where, like serine, where it was just an OH group. So it is neither acidic nor basic, but it is hydrophilic. So just understand how to find these features in the side chain, and we will apply these ideas later. So I keep hinting at stuff you need to know later, because I don't know, it's my nature to do that. But for now, just know that it's acidic if you've got a carboxylic acid in the side chain. The side chain is basic if it has an amine group. If you see any nitrogens, it is basic. Your work is done. That's all you have to do. And then you've just got to add the extra detail of, well, if it's acidic, it's a negative, and if it's basic, it's a positive charge. That's all it comes down to. Alright, so that is all of the side chain properties. So I'm just introducing them here. We will apply them later. So I will try to remind you of them when they're needed. Very important for the next section. In the next video, they're not going to come up too much. Our friend cysteine will come back because there's something special that it can do, and we'll talk about that. But otherwise, this is going to be really important for when we start talking about proteins as a whole, as a 3D structure. All right.